In previous screencasts, we learned that the properties of different compounds depends on the type of bonds that hold those compounds together. In a molecular compound, not only is the type of bond important, but the shape of the molecule is also important. In order to determine the shape of different molecular compounds, we need to learn more about the VSEPR theory. VSEPR stands for valence, shell, electron, pair, repulsion. And this is a theory which states that electron pairs will tend to repel each other in order to get as far apart from each other as possible. By arranging themselves as far apart from each other as possible, the electrons that are in bonds, as well as the unshared pairs of electrons, will allow us to predict what the three-dimensional shape of different molecules are. There are 5 different molecular geometries, or shapes, that we'll be learning this year. The first shape is called a tetrahedral shape. In a tetrahedral molecule, there are 4 bonded atoms around a central atom. Methane is an example of a tetrahedral molecule. In methane, you have 1 central carbon atom, and you have 4 atoms that are bonded around the outside. Now, if you look at this structural formula on a piece of paper, which is in 2 dimensions, it appears that the bond angle between the hydrogens is 90 degrees. But remember that molecules take up a 3-dimensional space. In order for the electrons that are being shared in those chemical bonds to get as far away from each other as possible, those hydrogen atoms can actually rotate so that the molecule can take on a 3-dimensional shape. The bond angle between the hydrogen atoms is actually 109 degrees. A second common VSEPR shape is called trigonal pyramidal. In a trigonal pyramidal molecule, there are 3 bonded atoms around a central atom. So ammonia is an example of a molecule that has a 3-dimensional trigonal pyramidal shape. If I look at the structural formula for ammonia, you'll see the nitrogen in the middle, and there are 3 bonded atoms around that central nitrogen atom. But the nitrogen also has a lone pair of electrons that causes that shape to distort. So that lone pair of electrons actually takes up more 3-dimensional space than the electrons that are in chemical bonds. So the angles between the hydrogens, instead of being 90 degrees like you see in the structural formula, and instead of being 109 degrees like they were in the tetrahedral molecule, those hydrogen atoms will be squished slightly closer together to form a bond angle between the hydrogens of 107 degrees. A third common shape is called bent. In a bent molecule, there are 2 bonded atoms around a central atom. Water is an example of a bent molecule. If I look at the structural formula for water, there are 2 bonded hydrogens around that central atom of oxygen. Notice that the oxygen also has 2 lone pairs surrounding it. As with the ammonia, those lone pairs of electrons take up more 3-dimensional space than the electrons that are bonded to the hydrogens. And so that's going to cause even more repulsion, and it's going to push those hydrogen atoms a little bit closer yet, to a bond angle of about 105 degrees. Notice the commonality between these 3 shapes. All of them have 4 pairs of electrons surrounding the central atom. The differences between them is the number of bonded pairs of electrons versus the number of lone pairs of electrons, those that aren't shared in a chemical bond. So a tetrahedral molecule has 4 atoms and no lone pairs. Trigonal pyramidal has 3 bonded atoms and 1 lone pair, whereas bent has 2 bonded atoms and 2 lone pairs. These lone pairs of electrons make big differences in the 3-dimensional shape of the molecules. A fourth shape is called trigonal planar. In a trigonal planar molecule, there are 3 bonded atoms around a central atom. So here you have 3 fluorines surrounded by the central atom of boron. Different than nitrogen, however, there are no unshared pairs on the boron. Although the structural formula shows that it appears that these fluorines are 90 degrees apart and the top fluorines are 180 degrees apart, if I want those electrons that are in the chemical bonds to get as far away from each other as possible, I need to create a shape that has bond angles of 120 degrees. So there would be 120 degrees between each of the atoms in a trigonal planar shape. The last shape is called linear. In a linear molecule, there are normally 2 bonded atoms around a central atom. In carbon dioxide, we have a carbon atom, and we have 2 atoms that are bonded to it. Now notice it doesn't matter how many chemical bonds are between the two. It only matters how many atoms are actually bonded to the center atom. And in a linear molecule, there are no lone pairs on the central atom. Notice there are lone pairs on the outside, but there are none on the center to distort the shape. And so this bond angle will be 180 degrees between the two atoms on the outside. The last section of this chapter deals with the intermolecular forces that occur between different molecules. So an intermolecular force is an attraction between different molecules which holds those molecules together. Sometimes this attraction is also called a van der Waals force. In the diagram, you see two molecules of hydrogen chloride. The chemical bond between the hydrogen and the chloride is called an intramolecular bond because the bond is within the molecule. In this case, it's a covalent bond that's really strong. The intermolecular force between those two molecules is represented by the dotted line. And compared to the covalent bond, this intermolecular force is very weak. The reason these intermolecular forces are important is because they affect the boiling point of the substance. Just like we learned in previous screencasts, the type of chemical bond that holds the atoms together determines many of the properties of the substance. The same is true for intermolecular forces. The types of intermolecular forces that are present will determine the different properties of the substance. Those molecules that have very strong intermolecular forces will have very high boiling points because it will require a lot of energy to break those intermolecular attractions. Whereas a compound that has very weak intermolecular forces will usually have a very low boiling point because it's easy to break those intermolecular attractions. There are three types of intermolecular forces. The first type is called a London dispersion force. A London dispersion force is also called an induced dipole. How this works is in a fluorine molecule, we have a non-polar chemical bond because the electronegativity of the two fluorines is exactly the same, and the electron cloud will be equally shared between those two atoms. But those electrons are constantly moving around, and so by some random chance, it's possible that you have a little bit heavier electron density around one of the fluorines than the other. When this happens, we create something called a temporary dipole, where one side of the molecule has a partial negative charge and the other side has a partial positive charge. But this is instantaneous. It happens just for a split second, so we call it a temporary dipole. Now, if this temporary dipole comes near another fluorine molecule, it can actually force that fluorine molecule with its even distribution of electrons to become lopsided. And so this dipole that forms is called an induced dipole. So the random motion of the electrons causes a lopsided cloud that forms just for an instant. And if that lopsided cloud, that temporary dipole, comes close to another fluorine molecule, it can actually induce another dipole. And then there is an attraction between those positive and negative parts of the molecule. London dispersion forces are found between all types of molecules, both polar compounds and nonpolar compounds. But in a nonpolar compound, the London dispersion force is the only intermolecular force that will be present. Because these dipoles are temporary, that attraction is only going to hold for an instant, and so this intermolecular force is a very weak attractive force. And that weak attractive force will result in compounds that have a very low boiling point. These types of compounds often exist as gases or as liquids that evaporate very quickly to change into gases. The second type of intermolecular force is called a dipole-dipole force. The word dipole means that you have a molecule that has two partially charged poles. A partial positive pole, which is represented by this lowercase delta and a plus sign, and a partial negative pole, which is represented by a negative sign. These partial charges cause that hydrogen chloride molecule to behave like a magnet, where the hydrogen chloride on the left will be attracted to the hydrogen chloride on the right through an intermolecular force between the positive and negative poles of each molecule. This type of intermolecular force is present in all polar molecules. So whereas a nonpolar molecule had only London dispersion forces, all polar molecules will have London dispersion forces and dipole-dipole forces. These partial positive and negative poles are no longer temporary as they were in the London dispersion forces. These are permanent, lopsided partial charges in the molecule. So because the molecule will always have a lopsided electron cloud, there is a stronger attraction between the compounds, and that results in a higher boiling point than nonpolar compounds. The last type of intermolecular force is called a hydrogen bond. Now don't be confused by the wording. Even though it's called hydrogen bonding, it is not technically a chemical bond. A hydrogen bond is a type of intermolecular force between two different molecules, rather than being a chemical bond within the same molecule. Hydrogen bonding is found when a polar molecule has a hydrogen atom that is bonded directly to a fluorine, an oxygen, or a nitrogen. For example, in the picture on the left, I have hydrogen sulfide, which has the chemical formula H2S. This is an example of a polar molecule, where the sulfur is more electronegative than each of the hydrogen atoms, and so the electrons shift up towards that sulfur atom, creating a partially negative pole. The electrons are shifting away from the hydrogen, making the hydrogen partially positive. The hydrogen atom of one hydrogen sulfide is then attracted to the sulfur atom of another hydrogen sulfide. That is an example of a dipole-dipole interaction. Whereas in hydrogen bonding, here I have a hydrogen atom that is directly attached to an oxygen atom, and that creates a very lopsided cloud where a lot of the electrons are hanging out around the oxygen, making it partially negative. That negative portion of the electron cloud is then attracted to a neighboring positive pole of a nearby molecule. This type of attraction is called the hydrogen bond. Because of the big difference in electronegativity between the hydrogen and the fluorine, oxygen, or nitrogen atoms, this creates an even stronger attraction than the dipole-dipole intermolecular force. So compounds that have hydrogen bonding will have unusually high boiling points. If I look at this graph on the right, the molecules that are listed along the black line are all examples of nonpolar molecules that have London dispersion forces. So they will have the lowest boiling point of all of the compounds on that graph. Notice as I move down the carbon group, from carbon to silicon to germanium and then tin, the boiling point of those compounds gets slightly higher. The same should be true for the molecules that are made from atoms in groups 5, 6, and 7. But you'll notice the first boiling points are a lot higher than would be expected. We would expect water to lie somewhere in here, but the boiling point for water is significantly higher. That higher boiling point is due to the presence of the hydrogen bonding between the water molecules.